Welcome to my video lecture series on fundamentals of physics. In today's talk, we will discuss vector algebra, the concluding part, part 2. In the earlier talk, we have discussed the vector algebra. We started with the geometric picture of vector, how addition of two vectors can be defined geometrically, the negative vector concept, and the scalar multiplication. Then we learn how to resolve vector in 2-dimensional and 3-dimensional Cartesian space. We introduce various terms like null vector, unit vector, magnitude or modulus or norm of a vector, and discuss addition and subtraction of vectors. There is a typos here. And the scalar multiplication. Today we continue with the discussion on vectors. So far we have defined addition and subtraction is achieved in terms of addition with negative vector, and another operation called scalar multiplication that involves that a vector is multiplied by a scalar quantity. Now in addition to addition of two vectors, we can define the operations which we call product operation. There are two kinds of product operations defined for the vectors. First we will take up what is called dot product or inner product or scalar product of two vectors. Dot product of two vectors is very easy to define if you know the magnitudes of this vector and the angle the vectors makes with each other, and let theta be the angle between the two vectors A and B, and magnitude of the first vector is magnitude A, that of the second vector is magnitude B, and theta is the angle between them. Then by definition the dot product A dot B is product of the magnitude of two vectors with the cosine of theta. And since you can treat the magnitude A cosine theta as the projection of vector A along the direction of the vector B, so sometimes it is called that dot product is by definition equal to the magnitude of the vector B and the magnitude of the projection of vector A in the direction of B. So that is the basic definition. A dot B is equal to magnitude of A magnitude of B times cosine theta. You can understand it also in terms of the components when we express the vector A as AXI plus AYJ plus AZK. So AX and AY and AZ are called projection of the vector A along the three axes X, Y and Z axis respectively, and similarly B can also be resolved into components of projection. BX, BY and BZ are components of the vector B. AX, AY and AZ are components of the vector A along the X, Y and Z axis respectively, and it is given that the angle is theta. Now with this basic definition, when it is applied to the unit vectors, you know that I dot j will be equal to 0 because cosine of 90 degree is 0. So I dot j is 0, and on the same basis we can check that since x axis is perpendicular to the z axis also, so I dot k would also be 0, j dot I and j dot k would also be 0, k dot I and k dot j would also be equal to 0. So these 6 combinations of dot product out of ijk will have a 0 value because the two vectors involved here are unit vectors, so having unit magnitude, but cosine of theta is involved in the definition and the angle is 90 degree, so you get I dot j, I dot k and such terms as equal to 0. But I dot I will be unity because cos 0 is unity and we are dealing with the unit vectors, so I dot I equal to j dot j equals to k dot k equals to 1. So we determine A dot B by using this technique. Then since we know about all the 9 terms appearing, 6 becoming 0, 3 non-zero or equal to unity, and so we get this formula that A dot B is equal to the product of x component of a vector and y x component of the vector b plus the y component of the vector A and y component of the vector B plus z component of the vector A and z component of the vector B. So A dot B can be defined as AX BX plus AY BY plus AZ BZ. So respective components, the product is taken and then we take the sum in all the three terms obtained in this manner. So that's how we can determine A dot B. But A dot B is a very useful quantity in understanding the direction cosines. In yesterday's lecture or last lecture, I did not describe the components of a vector in 3 dimension in the same manner as I have done it for the 2-dimensional case. Here I am giving you the picture that suppose we have a 3-dimensional vector A. In 3 dimensions we have chosen the x-axis and y-axis, they make a plane, xy plane, and the x-axis is once chosen, the y-axis will be a positive 90 degree and a line which is perpendicular to this is chosen as z-axis, but the sense of direction of the z-axis would be taken positive by the right hand screw rule, which was defined yesterday, that if you rotate the screw from right-handed screw from x to y, then the direction in which the screw advances would be the direction. So by holding it normally to the xy plane, if you rotate a screw, then the direction in which it will advance would be taken as the positive z direction. So that is the definition. Here the vector A can make and is making angle with all the 3 axes. Let the angle which it makes with the x-axis is alpha, let the angle which it makes with the y-axis be beta, and that it makes with the z-axis be denoted by gamma. Then we know that we can determine the projection in the same manner as we did in case of 2-dimensional vectors, that the projection of vector A along the x-axis would be the magnitude of vector A times the cos of alpha, and similarly the projection of vector A along the y-axis would be magnitude of vector A into cos beta, and that along z-axis will be the magnitude of the vector z into cos gamma. And here therefore we define terms called cos alpha, which is equal to A dot I, because A involves AXI plus AYJ plus AZK, and when you talk dot products, then the 2 terms which have J and K, the dot product will be 0, and the A dot I is nothing but the x component of the vector A or the projection of the vector A along the x-axis. So what we find, cos alpha is the x component divided by the magnitude, and similarly cos beta and cos gamma can be obtained by the y component of the vector divided by the magnitude and z component of the vector divided by the magnitude. Or you can write and express or obtain using dot product the x, y and z component. X component can be obtained by taking a dot product with I cap, y component can be obtained by taking a dot product with the j cap, and the z component can be obtained by taking a product with the k cap, which are the unit vectors along the x, y and z direction respectively. These angles alpha, beta and gamma are the angle which the vector is making with this axis, and the cosine of these angles are known as direction cosines. So directions cosines are nothing but cosines of the angles which vector makes with the 3 axes, and it can be very easily shown that the square of the direction cosine, when you add you get 1, which means cos square alpha plus cos square beta plus cos square gamma equal to 1. In case of 2 dimension, we will be having only 2 terms. If you consider 2 dimension in the similar manner, cos square alpha plus cos square beta, but in that situation beta will be 90 minus alpha, and this will become cos square alpha plus cos square of 90 minus alpha, which is sin square alpha, and so it is the same relation which we have used there, cos square alpha plus sin square alpha equal to 1. The direction cosines are very important in this manner, and you find that using direction cosine you can obtain the x component, y component and z component. If you drop a perpendicular from the point where the vector A is terminating on the xy plane, that point would lay at a certain point which will have a position vector AXI plus AYJ and no z involved, because it is the equation of the xy plane is z equal to 0. Earlier we have discussed that x equals to 0 was a line and y equal to 0 was also a line. X equal to 0 was the line called y-axis, and y equal to 0 was a line called x-axis. But in this case, z equal to 0 represents in 3 dimension the plane xy plane, and similarly y equal to 0 represents xz plane, and the x equals to 0 represents yz plane. So remember that the 2-dimensional Euclidean geometry and 3-dimensional Euclidean geometry are different, but are generalization. And so from 2 dimension you can generalize the 2-dimensional geometry and can obtain the 3 dimension in the manner in which I have discussed. So we could write that the position vector in 2 dimension, once you know, you can extend and include one more axis and write it in terms of 3 dimension. That is what I am meaning by the term generalization here. So we have understood the direction cosines. Let us work out one problem for the direction cosines. Suppose a vector is given as minus 2i plus 3j plus k. So that is the expression of the vector which is given to you. That vector A can be written as minus 2i cap plus 3j cap plus k cap. In that situation, you can find the magnitude of the A very easily, and that will be obtained by squaring each component. So minus 2 square plus 3 square plus 1 square and adding. So squaring each component and adding. So you get minus 2 whole square plus 3 whole square plus 1 square, and that turns out to be 14 when it work out, because minus 2 square is 4, 3 square is 9 and 1 square is 1. So 4 plus 9 plus 1 14. Take the square root of that. It will be equal to the modulus or magnitude of the vector as defined in the last talk, that magnitude of A is whole under the square root, the term which I am now saying ax square plus ay square plus az square. So ax square plus ay square plus az square, the whole under the square root, will give you the magnitude of vector A. And so it's an easy exercise. What you need to know only to calculate the squares, which is a simple mathematical operation. Multiply the number by itself, and you must also know how to calculate the square root, I hope, which you have learned in school. So we can find that modulus of this particular vector which is given here in the question is 3.7, and hence the 3 direction cosines can be very easily now obtained, because cos alpha will be a dot I, and a dot I will give you minus 2 because that is the x component. So a dot I or x component is minus 2 and divided by 3.7. So you get cos alpha value equal to minus 0.54. Similarly, you get the cos beta value, and the y component is 3. So a dot j is 3, and 3 divided by 3.7 is 0.81. So you can get the cos beta value also, and you can get the cos gamma value in the same manner. The component is 1, so it is 1 upon 3.7, and which gives you 0.27. So now you know it very clearly that if you take the square of these 3 numbers and add, then definitely you will get the 1. Cos square alpha plus cos square beta plus cos square gamma would definitely be equal to 1, which you can try. Now another example to understand the dot product. Suppose you are given 2 vectors and it is said that find the angle between these vectors. So by using the dot product, we can find the angle between 2 vectors if the vectors are given. Here 2 arbitrary examples have been taken, where the vector A is given as minus 2i plus 3j plus k, the same as I used in the earlier problem, and the vector B is I plus 2j plus 2k. Now to determine the angle between the vector A and vector B, what I do? First I determine A dot B. And so A dot B can be obtained by multiplying the component and adding them, the 3 terms. So x component Ax is minus 2 multiplied with the x component of B, which is only 1. So you get minus 2 from x component, and similarly the y component of the vector A is 3 and y component of the vector B is 2. So you get 6 from there, and then you get another factor of 2 because x component of A is 1 and the z component of A is 1 and z component of B is 2, so you get 2 here. So that has been explained how we carry out the dot product. It is very easy, or you can remember in terms of this relationship Ax Bx plus Ay By plus Az Bz. Ax is minus 2, Ay is 3, Az is 1, Bx is 1, By is 2 and Bz is 2. So it is very easy to read given the expression, the components, and once you know the component, it is very easy to compute the dot product, and which we have calculated here equal to 6. We can also determine by this formula which was earlier explained the magnitude of A, and in fact we have already determined in that case the magnitude of A turns out to be 3.7. But similarly you can determine magnitude of B. The x component square gives you 1, the y component square gives you 4, and the z component square also gives you 4, because the x component is 1, y component is 2, and z component is 2. So you have the square root of 9, which you know it's very easy, and that is equal to 3. So now you know all the three quantity ones, A dot B, magnitude of A and magnitude of B. Then by definition we know that A dot B is equals to magnitude of A into magnitude of B into cosine of theta. This is the defining relationship. So we can find cos theta from this formula, and cos theta, if you know, then you can find theta by taking cos inverse. So I have written directly the expression that theta will be cos inverse of A dot B divided by magnitude of A and magnitude of B. I substitute the three values obtained earlier in this problem, 6, 3.7 and 3. So 6 divided by 3.7 into 3, you work it out, and then you find that this is cos inverse 0.54. And cos inverse 0.54, you can check from the tables, it is 57.3 degree or 1 radian. So these two vectors which are shown here or given here are subtending an angle of 1 radian or 57.3 degree with each other. So you find that dot product is a useful operation in determining the angle. But alternatively, question can be said in this manner also, that one vector is given, the another vector, some parameter p is not given to you, and it is asked that what should be the value of p so that the two vectors are perpendicular. If the two vectors are perpendicular to each other or orthogonal to each other, then their dot product must vanish, as pointed out earlier, because cos of 90 is 0. So determine A dot B in this particular case when A is given as minus 2i plus 3j plus k and B is given as 4i plus 6j plus 5k pk. So I determine A dot B, and then I find that by doing the calculation in same manner, minus 2 into 4 gives me minus 8, 3 into 6 gives me 18, and 1 into p gives me p. So A dot B is equals to minus 8 plus 18 plus p, and this should be 0 because the two vectors are orthogonal, and you have to determine the p which makes two vectors orthogonal. So minus 8 plus 18 plus p equals to 0. So p plus 10 equals to 0 or p equals to minus 10. The problem is solved. And in alternative manner, you can be given a problem where the vectors given are so chosen that they are orthogonal to each other. So here in this question, the two vectors are given which are so chosen that they are perpendicular to each other, and you have to show that they are perpendicular to each other. Very easy exercise. Just determine A dot B and you will find that A dot B equals to 0. That definitely proves, and since neither magnitude of A is 0 nor magnitude of B is 0, so one can say if A dot B is 0 and none of the vector is the 0 or null vector, then definitely the two vectors will be perpendicular to each other. So very easy problems can be designed involving just dot product. Remember, many of the intricacies of the vector algebra we would learn when we will make use of it in our subsequent lectures, which are not on vector algebra but on kinematics in 2 dimension and 3 dimension, Newtonian mechanics and onward. These quantities will be useful for long period of time, and in fact in principle in entire curriculum which I will be discussing. Now another kind of product can also be defined, which is called cross product or outer product or vector product of vector. So where the dot product gives you a scalar, as you have noticed, every time I have determined A dot B here, A dot B is a scalar quantity because all the three things which involved here are numbers. So magnitude of A, magnitude of B and cosine of theta. So A dot B is a scalar quantity, and that is why the name scalar product is also given. Now to understand the cross product, it is not a scalar quantity, but cross product of two vector is a vector quantity. And the vector A is given and vector B is given, then you can find the cross product of vector A with the cross product of vector B, and if you know the angle theta, that can be determined. Just like we have defined A dot B as equals to a scalar quantity equal to magnitude of A, magnitude of B cos theta, we say that the magnitude of the cross product of A cross B is magnitude of A times magnitude of B times sine theta. So instead of cos theta which you have in dot product, here you have a sine theta. But that gives you only the magnitude of vector A cross B. Now you have to define the direction of A cross B. That is also given by definition chosen, and since we work with the right-handed systems only, so the direction of A cross B is appropriately chosen based on right-handed system of Cartesian space. And so what we do, that we say that the direction of A cross B will be perpendicular to the plane in which both the A and B. If there are two vectors, they definitely lie in a plane, and the direction of A cross B would be perpendicular to that particular plane, and perpendicular to that particular plane will have two sense of direction. So which direction, sense of direction it will have, that is determined again by the right hand screw rule, that if you rotate the right hand screw in the direction from A to B, because A is appearing first in the cross product, so from A to B, then the direction in which the screw advances will be the direction of A cross B. And definitely from this convention which we have chosen, the sense of the direction determined by right hand screw rule, if I am rotating from A to B and if it is clockwise or anti-clockwise, then the rotation from B to A would be opposite. In the diagram shown here, A to B is anti-clockwise and the direction of A cross B is the upward direction, which is shown here by unit vector n. This direction and is shown as an unit vector. So A cross B in this case will be pointing towards here, but B cross A will be pointing in opposite direction, because if A to B it is anti-clockwise, then B to A it is clockwise, so it will point in opposite direction. Now the magnitude are same, and that's why we say that the cross product of the two vector is not commutative, and you have to be very careful therefore in evaluating cross product, because the order is very important. In case of dot product, that is not true, and we can have easily. Now to understand the cross product in terms of the components, we can express A and B in terms of the components. A can be written as AXI plus AYJ plus AZK, and B as BXI plus BYJ plus BZK as used earlier. And then we know that we have 9 such combinations of cross product also. In case of dot product, 6 quantities become 0. Here only 3 quantities become 0 out of 9, and that is because the theta angle appears and sine of 0 is 0. So we find the cross product of I with I is 0, or I cap or unit vector along the x-axis when taken cross product with the unit vector along the x-axis itself, then the 0. In fact, any vector if you take its cross product with itself, then would be 0. Whereas any vector, if you take its dot product with itself, it will give you the magnitude square or norm or square of the magnitude or modulus of the vector. So here I cross I or j cross j or k cross k becomes 0, but then the 6 combinations we have to understand, and the manner in which we have chosen z axis I cross j. So if you take cross product in this manner, unit vector x axis I cross unit vector along y axis j, then that will be a unit vector along the z axis. I cross j is k. But if you change the order, so j cross I will be minus k, or you can write I cross j equals to k, and which is equals to minus j cross I. In the same manner, from that diagram of xyz axis, you can verify that the rotation of the y axis to the z axis will give you the positive x axis, and therefore j cross k is I and minus k cross j is I. And in the same manner again we can check that k cross I is j and equals to minus I cross k. And you can remember in this manner that you can write ijk. So cross product of I and j, ijk, so it's k, then that of jk, so next I will appear, so I, and that of ki will be j, so the next in sequence. But in this sequence ijk if you write, then you can read it. In some books you may find that they write ijk on a circle, and when you rotate from say ijk are written in such a manner that from I to j it's clockwise, and from j to k it's clockwise, and from k to I it's clockwise, and then they say that I cross j will be k, and if you move along the clockwise in this manner, then it will give you the positive, the remaining, so I cross j will be k, but if you have to move in the opposite direction, j cross I, it will be minus k. So you can remember it in any manner you want. but the basic point is that we know now all the 9 expressions, so we can resolve the 8 by using the components of vector. So there will be 9 terms, out of which 3 will become 0 and remaining 6 can be clubbed. And so we have 2 terms involving I cap, 2 terms involving j cap and 2 terms involving k cap. And the result of A cross B, when you work it out explicitly, to save time in this presentation I am not doing it explicitly, but you know that I will appear when there will be a by j will be taken cross product with bz k, and since a by j bz k, since j cross k will be involved, it will be positive I. Another involvement will be that when AZK is taken with the B by J, but then it is K cross J, so minus I. So we have A by BZ minus AZ BY here with the I cap, and similarly with the J cap you can understand that the J would be involved in 2 terms, this particular AX BZ, but AX BZ is I cross K and I cross K is minus J, so I cross K is minus J, so AX BAZ is written here with minus sign. Another involvement will be that when you have the AZ BX, and that is K cross I, so plus I, so AZ BX is written here. In the same manner you can complete that for the K, from where you will get K, you will get K from AXI BY J, so AX BY, that is positive I cross J, and another from A by J and BXI, and that is A by BX, it would be negative. So we could make out that A cross B is AY BZ minus AZ BY times AI, and AZ BX minus AX BZ times J, and AX BY minus AY BX times K, as shown here in the picture. So remember, A cross B will not be equal to minus B cross A, and the directions would change automatically. So if you look at this formula also, then if you replace A by B, then you will find that if you make a replacement of A by B, then what you are getting, so you are getting its sign reversal, because if you replace A by B, this will become B by AZ, so like the previous this term, and so the sign reversal is there when you replace A by B. So if you change the order, the direction or sign will change in the opposite one. Now you can write A cross B and determinant form also. If you know how to evaluate the determinant, to evaluate a determinant we can use this row IJK row as a to open up the determinant, and we can use it if you understand what we call cofactor. Cofactor of I, for example, is that don't consider this row of I and column of I, so you are left with this, and in this cofactor the value is evaluated in this manner, AY BZ minus AZ BY. So you can write that formula which we are having in this manner called determinant. So from here you get I cap AY BZ minus AZ BY. For J cap you have to consider this here on the other side. So for J cap similarly you have AZ BX minus AX BZ. For K cap you have AX BY minus AY BX. So in this manner you can obtain by using determinant also. I have shown it by giving an example. Suppose A is 2I minus 3J plus 4K and B is I plus 2J minus 3K. So I can do it by identifying the component also, and I can do it explicitly by doing it in 9 terms involving it and so on. So A dot B is very easy to determine. The 2 into 1 minus 3 and 2 and 4 and minus 3, so these are taken here, 2 into 1 minus 3 into 2 minus 4 into 3, and A dot B in this case turns out to be, for this example, minus 16. But A cross B can be obtained by writing it in determinant form. So I would write 2 minus 3 4 the A, and 1 2 minus 3 the B and IJK. And then if you know the how to calculate the determinant, then it can be using cofactor. So cofactor of I would give you I times minus 3, so 9 minus 4 and 2 8, so 9 minus 8I. Cofactor for J 4 into 1 4 and minus of minus 3 into 2, so 4 plus 6J, and for the K 2 into 2 4 and minus of minus 3 into 1, so 4 plus 3K. So we could evaluate it here. It's very easy calculation, but you have to do a few questions so that you remember how to do it, and as well as you do it correctly. And especially if you are using determinant, you must check it n number of times for giving you sufficient practice that you don't commit a mistake in evaluating by the determinant form. But it's quite easier to remember cross product in this particular form. Now it's very useful operation, and if you have two vectors A and B, then they define a parallelogram in which the two vectors A and B are the two sides of a parallelogram, and by adding the two other sides you can complete the parallelogram shown here. So two vectors A and B describing the two sides of a parallelogram, since this will be parallel and of same value and this will be parallel to the same value, so you know that this is a parallelogram. And in this parallelogram, if two vectors are making an angle theta, the A and B, so this theta can be anything. Theta equal to 0 will not make sense because then A and B are collinear and the area of parallelogram is 0, and it is not called parallelogram in that case. And so non-zero value of theta is there. A and B are given. Then you can determine area of this parallelogram. But an interesting aspect of physics is that area is taken as vector quantity, and the first such definition of the area vector is given here, that area of a parallelogram by definition is equal to the cross product of A and B. So it would be a vector which will be having area magnitude equal to the area magnitude of the area, and direction will be perpendicular to the plane containing A and B. So that is how we obtain the area. And often in the physics course, area would be used as a vector quantity unless otherwise specified, and we are ignoring the directions or not required to consider the direction. Otherwise, area is a vector quantity. Dimension of area definitely from this formula, because A and B are sides or having dimensions of length, and therefore dimension of area will be L square. Now the same formula you can use for obtaining the area of rectangle, because rectangle is a special case of parallelogram, and in case of rectangle the theta is 90 degree. So theta is 90 degree, so sine 90 degree is 1. So the area of a rectangle, the magnitude of the area of rectangle will just become product of side, which you may have already learned in school courses. Now you can also obtain the area of square also, because square is a special case of rectangle when two sides are equal, and so in case of square the area of a square will be given by square of side, and that's why the name square has also been chosen. So the area of a square is side square, area of a rectangle is the product of sides, and area of a parallelogram is given by A cross B. It's an important learning from this vector algebra. Now to do the numerical problem, here the two vectors A and B are given, and you have to determine the area of the parallelogram. So the same determinant approach I am using. I have substituted the values of A and B here. The x component of A is -2, y component is 3, z component is 1, as clear from the example. X component of B is 2, y component is +6, and the k component is 2, and then I calculate. So I, the coefficient will be 3 into 2, 6, -6, so 0. So there will be no I component in A cross B because it's vanishing. The j component, so 1 into 2 minus of -2 into 2, so it becomes 2 plus 4, and it's a 6j. And k component similarly -2, 6, so -12, minus 3 into 2, 6, so -12 minus 6, so it is -18k. So you get that the area of parallelogram for having a parallelogram which is having vector A and vector B given here as side is equal to 6j minus 18k from the across B, and the magnitude you can obtain by squaring 6, you get 36, by squaring 118 you get 324, and the 2 adds up to 360, and the square root of 360 you can determine, and that is 19 here. So 19 meters square is the area, because it is given here that A and B are expressed using meter. So the area obtained will be 19 meters square in the magnitude, and if you divide this particular quantity by 19, so that would give you the unit vector direction. 6 by 19 j minus 18 by 19 k is the direction of unit vector of the area, and so area would be pointing in the same direction as A cross B. Now you can check before doing more calculation the properties that A dot B I have already said and explained is B dot A. The order is not important, but in case of cross product it is not so. A cross B is minus B cross A. But both dot product and cross product are distributive over vector addition. So A dot of B plus C, where the B plus C are having addition and you take dot product with them, can be expressed as dot product of A with the B and dot product of A with C and then adding them. So A dot B plus C can be written as A dot B plus A dot C. Such a property is known as distributive property. And we say that scalar product is distributive over addition. The opposite we are not saying, has making no meaning if you say that the addition is distributive over dot product, because dot product gives you a scalar. So such a thing would be meaningless thing. So remember, to express it correctly, the dot product is distributive over the addition of vectors, and so is true for the cross product also. A cross of B plus C is A cross B plus A cross C. In case of scalar multiplication also, if the constant is associated with A, whether you associate it with A or associate with the B, doesn't matter, and would be the same whether you associate it with the dot product. So these are the relationship we have for both the dot product and cross product. The scalar multiplication effect is shown here and the property is interesting. For you can define, because the cross product of two vector is a vector, you can take another product, and in case of cross product involving three vector, in cyclic manner, if you write this quantity A cross B cross C plus B cross C cross A plus C cross A cross B, then the sum would be equal to 0. And this theorem is known as Jacobi Identity, and it can be proved mathematically. So you can take any example of A, B and C and work it out. However, that would be a lengthy calculation because you would have to determine several cross products. First A cross B, B cross C, C cross A, and then the obtained three values, again you have to determine their cross product with one of the quantities out of A, B, C. So a lot of work there, but it can be established that this is equal to 0 and it is known as Jacobi Identity. Now we can define triple product also, as the triple product of cross product already discussed in terms of Jacobi identity. If B cross C is a vector, and if you take a dot product with another vector A, then that is called triple product or scalar product. Triple scalar product of three vector is defined as A dot B cross C. A is given by this, we have already expressed B cross C in determinant form. So when you take the dot product, it becomes another determinant. Instead of having I, J, K, you are having Ax, Ay, Az here, but the determinant can be determined in the same manner and you can evaluate the triple product. So why triple product? Triple product is very useful in, just like the cross product was useful in defining the area, which is a vector quantity. We define volume of a parallelepiped, and volume of a parallelepiped is a scalar quantity and in physics, and it is defined in terms of triple product. So a parallelepiped, just like a parallelogram which has two sides A and B, a parallelepiped has three sides A, B and C, and here such a parallelepiped is shown in the diagram. And then one can evaluate the triple product A dot B cross C, and that would be giving you the volume of this parallelepiped. And in case of a parallelogram, you can define volume because it's a two-dimensional object, and a two-dimensional object has area only in Euclidean geometry. But here it's a three-dimensional object and we define volume by this. This is the definition of the volume here mathematically, that A dot B cross C, and its magnitude is taken, the magnitude of the scalar product, because we don't assign negative value to the volume. So magnitude of A dot B cross C is called the volume of parallelepiped. But you know that if it is cuboid, then in the cuboid the angles are 90 degree, and so you know that the answer would be that this A dot B cross C would reduce, because the angles whatever are involved are such, because B cross C, B and C are 90 degrees, so sin 90 is 1. But when you take the dot product, then the B cross C would also be in the same direction as A, because the three directions A, B and C are mutually perpendicular to each other in case of what is called cuboid or rectangular prism. So in case of cuboid or rectangular prism, because A, B and C are mutually perpendicular to each other, we find that if we evaluate this volume, the formula of volume will become simpler and the volume would become equal to the product of three sides. So length, breadth, height, whatever you call, the product of three sides will be equal to the volume. And cube is a special case of cuboid when the sides are also equal. So the volume will become the cube of the side, and that is the name cube. Cube of a side. A cube is having all the three sides equal and inclined at 90 degree to each other. Now some more understanding is required, and which is sometimes discussed, sometimes not discussed, but I wish to point it out so that in some book if you find the reference then you can understand. Sometimes you find two adjectives with the word vector, polar vector and axial vectors. So what are polar vector and what are axial vectors? So vector we have already defined and we have understood the vector and we know how to resolve them in x, y and z component. And you know that we have chosen the right-handed coordinate system. In the right-handed coordinate system we have adopted. But there is exactly a parity inverse system which is called left-handed coordinate system. Or in other words, instead of calling the positive x as the positive x direction, if you call the other direction, the negative x direction, as the positive x direction, and similarly for y and z. Or in very simple terms, if you make a transformation that you have an x, y, z axis like this, so this is the positive, now make the opposite of it as a positive x axis, y, so make the opposite of that as a positive y axis, z. So this is right-handed coordinate system, this is the left-handed coordinate system. The operation is called parity. Parity is a transformation, but it is an improper transformation. So in case of parity, what you get, that you cannot superimpose a right-handed and left-handed coordinate system on each other by any technique. If you try, then you know that the thumbs are pointing in opposite direction as I am showing here. So right-handed coordinate system and left-handed coordinate systems are opposite of each other, and they can be compared with the mirror images also. But I am not using here mirror image explanation, but the explanation in terms of that if you make parity transformation, then the position vector will change into minus r. The velocity vector, since it is defined as the rate of change of position vector, similar formula we have. The parity when operates on the velocity, it will turn it to the minus velocity, and same is the acceleration. So that is what, that if you are heading towards a mirror and approaching the mirror, then you will find that you are moving towards the mirror. So you are having that direction which is towards the mirror, but in the mirror the image would be coming towards you. So image would be coming towards you, so it will be having an opposite direction. In that manner you can understand this transformation, that the parity, if applied on the velocity, the direction would change. But now you may have noticed that for these vectors called polar vectors, which point to something, to a pole, or polar vector, the position vector, the velocity vector, the acceleration vector, under the parity sign is changing. But if you take any two quantities out of this, so if there are any two polar vector for which the direction is changing, sign is changing under parity, but if you take cross product, then that would also be a vector. But this cross product will not have any change of sign. So if P of A is minus A, P of B is minus B, when parity operated on A gives you minus A, when parity operated on B gives you minus B, but parity operated on A cross B will give you minus A cross minus B is the same A cross B. So these vectors A cross B are different, and in fact A cross B are different, as you will later realize when we will take up tensor in more serious manner. So P of A cross B is equal to A cross B. Such vectors are called the axial vectors or pseudo vectors. They are not in true sense vector, but are tensor of rank 2, antisymmetric tensor of rank 2, which will be explained later only. So I will not deliberate upon that, but I wish to point it out here that there are many quantities which we will be using and defining shortly, which are the axial vectors and not the polar vectors. The position and momentum are polar vector. Momentum will be defined as mass time velocity, so it's a polar vector. This is position vector is also a polar vector, but their cross product r cross p will be called angular momentum, and angular momentum is an axial vector. Similarly, r cross f will be defined as torque. F here indicate force. So that is called moment of force also, and its name is torque. Momentum is called angular momentum. And r cross f is also an axial vector, it's not a polar vector. Both r and f, because force is defined as mass time acceleration. So as I have said, r, velocity, acceleration, momentum, force, these are polar vectors. But angular momentum and torque are axial vectors, and so is the angular velocity. However, the appearance may not be very easy here because angular velocity would be defined by this relationship v equals to omega cross r, and similarly angular acceleration also. So these angular quantities which we will be defining in coming days would be also axial vectors or pseudo vector. And if you take any of this quantity like angular momentum here and take scalar product with that quantity, then the scalar which you will get will not be behaving like the scalar. So in case of scalar, for example, the mass, if you apply the parity, it remains m. But in this case, when you apply the parity of c, the polar vector is not changing. So it's minus c, or a cross b is not changing. So this would be changing. So as pseudo scalar it will be called. So if we take dot product of a polar vector with an axial vector, you will get a pseudo scalar and not scalar. That as pseudo scalar reverses its signs, remember, like a vector quantity. So it is behaving like scalar, but otherwise it's behaving like also vector as far as parity is concerned. So in all other terms it is a scalar, but in terms of parity it is called pseudo scalar because it is behaving like a vector as far as parity is concerned, or a polar vector as far as parity is concerned. So that a pseudo scalar reverses its signs when the coordinate axes are inverted or parity transformation is applied. Suggested that a pseudo vector is not the best object to describe a physical quantity, because if you consider the parity transformation, its value will change the sign. In three-dimensional space, quantity described by a pseudo vector are antisymmetric tensor of order 2 which are invariant under parity operation, and pseudo scalar are tensor of rank 1 which changes sign under parity. But we will be better able to understand these notions only when we take up the discussion on tensors in much better terms, and a detailed discussion on tensor would definitely be required at some stage of this series of video lectures. Now you can also define quadruple product, and quadruple product of two kinds are defined here. The scalar quadruple product of a cross b dot c cross d, the basic definition remains same, and so you can work out and you can very easily prove that a cross b dot c cross d is given by this determinant. And so this determinant involves all the four dot products here, a dot c, a dot d, b dot c, b dot d, and the determinant form. So you can find the scalar quadruple product also, and if you are so interested, you can find the vector quadruple product also, and the vector quadruple product you can prove that is related to the scalar triple product of ABD and times C minus that of ABC times D, scalar triple product. But I am not giving examples here because at this stage of the course we will not be requiring applications of scalar quadruple product and vector quadruple product. But once you have defined these dot product and cross product, you can introduce all such terms and the extension is quite easier. In case of differentiation, as I have pointed out it earlier also, that I, J, K unit vectors are independent, they do not depend upon time. It's not true in all cases, but in case of Cartesian space it is true, and so unit vectors are independent of time. So if you have to differentiate a vector A, you have to consider the differentiation of each component separately, and there is no need to have any term like the differentiation of unit vector with respect to time. Otherwise, a quantity which is being expressed as product of two, magnitude and direction in terms of unit vector, the differentiation formula for product of two would be involved. But here, since I, J, K are constant vectors, we have very simple relationship as written here, that the rate of change of vector A with respect to time t is rate of change of x component with respect to time t times I cap, rate of change of y component times t j cap, and rate of change of z component with respect to t times k cap. And the same can be extended to the integration also, because I, j, k do not depend, and so we have the similar relationship. You can determine the integration of vector A with respect to time t by determining integration of each of the components separately and then making substitution here. So this will not be true in the case of spherical polar coordinates, which we will be introducing shortly, and many other coordinate systems. The unit vectors do depend upon time or may be changing in time, and so since they are function of time, so their derivatives would also appear. When you derive or integration, you have to be more cautious in those cases. I wish to point out that I am not using at this stage several concepts which will be later on introduced, like concept of point function, fields, scalar fields and vector fields, vector calculus, where we will discuss gradient of a scalar field, divergence and curl of a vector field, and the other curvilinear coordinate system. I am concluding the talk in this particular talk, the vector algebra, and all these issues would be discussed at an appropriate stage in the series later on. So this cannot be considered as a standalone complete course on vector algebra and analysis, and it does not include vector calculus and fields. There are certain alternative definition of vector which I wish to make clear to you, and I hope that you should keep it in mind. However, we will be using whatever has been discussed so far, and this is just for understanding, because in some books you may find treatment in their terms. The definition of a vector can be given as n-Tuple, and n-Tuple means an n-dimensional vector A is an ordered collection of n real numbers a1, a2, a. So 3-dimensional vector A is ordered collection of 3 a1, a2, a3. If you write it in this manner, then this is called an n-Tuple, and in this manner the Hamilton introduced the concept of vector. An n-Tuple is known as monad for one dimension. So if you use only one number, then it's called monad. If your dimension is 2, which we have already considered, then the n-Tuple would be called pairs or twins. And when dimension is 3, then triad or triple. So 3 numbers you have are quadruple or tetrad when n equals to 4. So explaining in terms of triad, that vector A can be described by a triad like this, n-Tuple like this, ax, ay, az within the bracket, and the another vector B as bx, dy, dz within the bracket. And if you have to add, the same algebra would applicable, the x component will be added, so the new x component will be ax plus bx, new y component will be ay plus by, and az plus bz output the result of adding of two vectors. When you do the scalar multiplication, each component is multiplied by that scalar. So in this way also you can express the vector algebra, and as you know that you can express the position vector, instead of position vector you can specify the position by the coordinates. So whether you write the coordinates within the parenthesis xy, that is nothing but a pair or a twin, and therefore is a n-Tuple, and by using that n-Tuple you can express the position, or you can express the position in the way we have been expressing it in terms of components and unit vector. So the algebra remains same, so mathematically the objects are equivalent. Now another way of describing the vector is in matrix form. A n by 1 matrix is called a column vector, and a 1 by n matrix is called a row vector. So if you write in matrix say a1, a2, a3, it's a row matrix, and if you have one below it a2 and a3, then it is a column vector. So the column vector matrix, it is n by 1, so there are n rows and 1 column, and the row vector matrix is 1 by n, so 1 row and n column it is having. Now the two products you can understand very easily when you express vector in terms of column vector and row vector. The dot product can be interpreted as a product of row vector into column vector. So 1 by n into n by n, so it will give you 1 by 1 after taking product, if you understand the matrix multiplication. I am not explaining matrix multiplication here, but if you know the matrix multiplication, then you know that by taking product of 1 by n and n by 1 matrix, you will get a 1 by 1 matrix, a number, and that is how dot product is defined when you express a vector in matrix form. And cross product can also be obtained, but in the opposite manner, that you have to take column vector with row vector. So earlier we have taken row vector and column. So column vector means, what is column vector? N by 1 first and then 1 by n. So when you multiply n by 1 by 1 by n, it will give you a n by n matrix. Then often in literature you will find that set of all three-dimensional vectors, which we have defined here in this class also, is called three-dimensional real space. So many times if you find this word three-dimensional real space or the symbol R3 shown here, this symbol, then that is nothing but a three-dimensional vector space or a space with set of vectors here. Earlier I have defined space also as a space of points. So a vector space is a set of vectors, and a set of three-dimensional vector is called three-dimensional real space, and its symbol is R3. There is an alternative way that instead of writing x, y and z, x is unit vectors like I, j and k, I can write them as the unit vector along the first axis, even along the second axis and third axis, denoted by E1, E2 cap and E3 cap respectively. So E1 cap is nothing but I cap, E2 cap is nothing but j cap, E3 cap is nothing but k cap. And I can similarly express the x component I can replace by A1, y component as I can write as A2, and z component I can write as A3, and then we can express the vector A in terms of component very simply by using this summation formula, that summation over 1 to 3 AI EI cap. So that's an easier way to do, and many sophisticated. When we will advance further in this series, then you will find that we prefer such sophistication symbol in expressing vectors at those stage. But right now that is beyond our discussion, and I have not talked about many things because this is a very important concept. First thing which you must also know, that a vector is a very common word and it has different meaning. For example, in life science, when you say vector species or vector diseases, it has different meaning. It has a meaning in biotechnology or genetics. It has a different meaning in as a vector graphics. So this term is often used in many branches of knowledge, and the meanings are quite different. So one has to be very careful. The meaning which has been explained here is the meaning of vector, primary meaning of vector in mathematics or physics as used in mathematics as used in physics. So in this talk, however, there are certain rigorous level of our understanding of vectors, and which are very important for understanding the physics, but because at this stage the ideas cannot be explained in clear terms, and we have to learn first many things more, and then only we can appreciate what these things refers to. So just like I have said you that the marriage between algebra and geometry lead to calculus or what? Cartesian geometry, not calculus. So similarly, a marriage between geometry and calculus led to a new branch which is called differential geometry. And the topological space, metric space, normed vector space, contravariant and covariant vectors, the scalar and vector fields, the Jacobian and vector calculus, all these topics have been deferred. I am not saying I will not discuss these topics in my future lectures, but will be introduced at the appropriate level in the series. So far in this lecture, I have limited myself for the kind of knowledge which is required to understand the Newtonian physics or kinematics in 2 dimension and 3 dimension, which we will be talking shortly. And therefore, this is the concluding talk on mathematics of vector algebra, and in the next talk I will be talking about kinematics in 2 dimensions, and I will be considering certain examples describing kinematics in 2 dimensions. I hope that you are liking my lecture. Please click the like button. Please click the subscribe button to subscribe to my YouTube channel A for Science. Click the bell icon to get the notification regularly. And thank you for being with me in this series of talk on fundamentals of physics. Thank you very much.